Okay, right. So welcome back, everybody. Today we're going to talk about the six vertex model a bit more, and we're going to hopefully get to the coordinate answers for the six vertex model. But what I really want to focus on actually is some sort of diagrammatic notation that some people use and some people don't use so much. I really think it is amazing because I really think that it will be very helpful next time to make connection to the sort of the algebraic things that will be really nice for doing the beta ansatz in a much more efficient way and so on. So, and I think this graphical notation that I will develop is going to help us a lot with this. But let's first recall what we've been doing. So a little recap. So we were studying the six vertex model, and the goal was to compute the partition function. The partition function was the sum over all the configurations, and then the weight of each configuration. And I denoted the weight by some A to the number of A vertices, which I will draw in a second, B to the number of the B-type vertices, and C to the number of C-type vertices. And we chose a lattice on a torus, which I drew like this. And the number of lines in both directions can be different. This is a bit less. Okay, let me draw a few extra here. Okay, so K horizontal lines and L vertical lines. And these six vertices, they were the following. So I'm going to redraw these six pictures. I'm not going to put all the data in there that we had last time, but I'm going to put a bit of it. Okay, so let's first draw six different vertices.
You can.
So there are 2 points of view that I wanted to do. Actually, I forget which colors I did last time. So one were these little arrows on the edges, and they can, for instance, point to the right and up, or they can point to the right and down.
No.
Is there a problem, or is it okay?
I switched it back.
Or it can point horizontally inwards and vertically outwards. And then we can also have all the vertices where everything is precisely reflected. So to the left and down, or to the left and up, or horizontally outwards and vertically inwards. Right? And these little arrows were supposed to remind us where the protons were on the hydrogen bonds in this square approximation to standard ice. And another picture which I will use was by putting thick lines. And the rule is just, I'm going to just draw it and then we'll get back to this. This will be my, and then today I'm just going to draw it in white because you might have only one color. So what we do is basically whenever the arrows are pointing to the right or up, we don't put a thick line. And whenever they go the other way, we put a very thick line. So like this is a thick line. Here, the arrow, this thick line goes here and here. I'll get back to this rule in a second. And here is the opposite. So we swap the places where there are no lines, like everywhere here, and where there's a thick line. So then this looks like this looks like this, and this looks like this. Okay, so these were these paths. And we're thinking of these paths as starting from the sort of in the general this area, and then going towards this area. So the paths go in that direction. And then you see that these paths, there's either no path or there's one path, and it can go straight or turn. Then there can be two paths, and they can kind of touch. If we want, we can kind of think of them to kind of bounce off each other, like that. And then here we have paths that come from the left, and they either go straight or turn. And then the third type of degree of freedom was some sort of classical spin. It's some sort of variable which only has two values. So let's say it's plus for the arrows pointing where if there's no path, and a minus if there's a path. Right. So these are the six vertices of the six vertex model. Now these two were those that I called vertices of type A. So these are the ones that we count in our NA. These middle are the ones that we count for our B. And these ones where the paths turn, or the arrows have some sort of saddle point, let's say, they're vertices of type C. So we draw a configuration, we make sure that it only contains these vertices, otherwise we give it 0 weight. And then if it only has these vertices, we just count how often they occur, but we don't really distinguish. We make the zero field assumption that it doesn't matter whether we can flip paths and no paths, or we can reverse all the red arrows, or reverse all the plus and minuses. So that's the problem. We want to compute this partition function, and we will use diagrammatics for this. So let's try to do this. Maybe I should. Let's just start here. So diagrammatics. So there are a number of rules which are going to allow us to do computations by drawing pictures. And the rules are as follows. First, this is convenient. We're going to orient our rows and our columns of the lattice. So all the horizontal lines and vertical lines. And usually, actually always, but sometimes maybe I want to rotate these pictures a little bit later on and so on. So it's just good to kind of fix this for once and for all with these orientations. But usually, this will be to the right and up. Well, or up, I guess. And to indicate this orientation, we use it by a little arrow. So indicate. This little arrow should not be confused with the red arrow there, which I will not use much anymore. So indicate by a little arrow at the end of the line. So what I will do is I will draw my lines like this. This should not be confused with the spin up. It's just a line which kind of, here we think of it as going from here to there. So that's why there's an arrow like that, and there's also one that goes like that. But now, since I have this kind of stuff, I could, if I wanted, I could kind of draw this, and you would still know how the line is oriented. That's kind of the useful thing, how I'm supposed to think of going along this line. And then this path, which is the very thick line that we had before, is precisely if this little red arrow, so let me draw the red arrow, the one with the degree of freedom on the middle, goes against the orientation. Right, so this line had an orientation going to the right, and the red arrow points the wrong way, and then I indicate it by a path. So that's the rule that I use here to go from the red arrows to the thick paths. I basically already mentioned this last time. And note that if I'm going to if I'm going to draw, so now I want to kind of put these little orientations here, like that, everywhere. And note that I only put an orientation at the end of the line. So here, I think of these as two crossing lines of the lattice, and I'm not kind of drawing also this little orientation line here. It's just, you know, you go from here, then stuff happens, and eventually we go there, and it's enough to have the little arrow at the end. All right. So then, the second thing, which I've also already done, but I'm going to do it a little bit more carefully, and this is adapted to having only one color if you're taking notes. So last time I used more colors, but now I'm going to just use black and white. So these kind of spins, which, okay, this is the color because I used the color there, but it's not important, plus minuses, they're going to be drawn like this. I want to say a dotted line, which means, well, now I have to draw one more time my red arrow going with the line. So this means that no path. But here it was a little bit unclear whether there was a path or not. So I want to make completely clear that there's no path. So I'm going to draw a dotted, or I'm going to draw this thick path like I did before, if the arrow went along against the line by our previous convention. Right? So this is just because here, you know, maybe you didn't really see when I drew it and I wasn't super careful to draw it super, super thick. So now I would instead draw this line kind of dotted and dotted like that. and it will be slightly easier in your notes to do this. So for instance, you could first draw the lattice like I did here, and then kind of clarify whether it's supposed to be an empty line or a thick line. Then the third rule is that we're going to identify the vertex weights with their diagram. So for instance, I'm going to say that this diagram is going to be equal to this diagram, and it's going to be equal to A, which was the vertex weight, and I remind you from last time that physically this was e to the minus inverse temperature times the energy of the configuration at that vertex, right? So it was kind of a Boltzmann weight at the vertex. And then to do this consistently, I should also, for instance, what happens if I would have a diagram like this? Well, this is supposed to never occur in our lattice. And another example that's not supposed to occur is something like this. So I'm just going to give it weight 0. And since I identify the weight with these pictures, I'm going to say that these diagrams are actually 0. The physical interpretation, by the way, of this is, of course, that they are not allowed. So which you could kind of think of as setting their energy to be infinite. So just make it depenalize completely of this occasion, this situation ever occurring. Okay. Let me remove a little bit here at the bottom, because I want to see if I can hit it here and keep it up. Actually, I'll just redraw this later. And I don't need to write all the way at the bottom. So the next rule, I'll give some examples in a moment, but let me first write down all the rules. This is also no longer the recap. If you were writing sections, I guess this is supposed to be section 4.1. Okay, so now we're going to use summation convention for internal lines, internal edges. So graphically, if I have some stuff here, whatever it is, and then I have an edge, and then some other stuff, so typically there will be a vertex here, and then I don't know what's happening afterwards. But if there's an internal edge like this, then what I mean is, well, it's supposed to be a sum over internal spin configurations, plus or minus, sitting on that edge. And now graphically, I can use my notation for these internal spins. So this means that I have this with a dotted line, plus this with a thick edge in between. Okay, so whenever you see a an edge connecting two vertices, so it's internal, then you sum over it. And there's sort of a special case which we will need of this, which is related to the periodic boundary conditions. So just to spell it out, if we have a whole whatever, and then I will draw this little picture. By definition, this is the sum over the spin plus or minus on the outside. Like this. And we can again expand it graphically that it means dotted, lots of stuff, dotted, plus thick, lots of stuff, thick. Up and let's do some examples with this to see if we're all on the same page. But this will be super important. I will use it a lot today and especially next time. So make sure that you understand this. So look at the examples, and if you don't understand it, ask me or train with it a bit before next time. So for instance, if I draw this picture, so one horizontal row with these little kind of hooked things at the end, and then crossing two vertical lines. Well, then let's do it step by step. By rule 4, I see one internal edge here, right? This guy connects two vertices, so I'm supposed to sum over the possible configurations. So it's either a dotted line that goes in between, or let me put it below, a thick line that goes in between, and we sum the two possibilities. But now we also have a kind of an internal line, but wrapping around the cylinder on which it is drawn. So by the rule for periodic boundary conditions, we have to expand each of these again. So the top one has two possibilities. It's up, sorry, and I'm supposed to orient my lines. So there we go. So the top one has either looks like this, or it looks like this. And then the bottom one can likewise be expanded either like this, or with a solid line going horizontally and thin line. So note that in this example, I've fixed all the, since this line here is a completely closed line, so it's completely internal. So we sum over all the possible spins, classical spins on the thing. And so here you see that all the configurations on those horizontal edges, they have been fixed. But the vertical ones, they're not internal lines. They're just, they have some sort of, yeah, right? They're kind of like external lines. So we don't have a sum over the external lines. And that's why here we still have some external lines for which we didn't do anything. So let's make this example a little bit further. So let's assume that now actually these external lines were also fixed. So let's say we might have this. So the first external line was thick and the second one was very thin. Then we can use this here and now plug in these values there, and we will see what happens. So let's see. So one possibility was that the horizontal line was dotted. Then we have a thick line crossing it, and then another dotted line crossing it. The next possibility from this one here, well, it would have, let's actually draw it. We have a thick line coming in, then a thick vertical line, then a dotted line, then a dotted line, and then a thick line, like this. Well, and then we have two more options coming from there, so let's also just draw them. This, this, and then finally this guy here. There we go, like this. So these are all the options. This is what we get from our graphical computation. So now I just use the above. So I use rules 4 and 5. But then next I have the rule number 3, which said that I'm going to identify the vertices with their diagrams, the vertex weights. And remember, the vertex weights in the partition function, which disappeared, over A and A, B, and B, C, and C. So we multiply weights. So here, what we're reading off is, well, here we see a vertex of type B. And here we see one of type A. So this is B times A. Then the next one, well, this vertex is not allowed. So this is 0. Then this vertex here, they're also not allowed. They have 3 thick lines and 1 thin line around them. And then finally here we have an A and then a B. So in total what we're going to get is 2AB. So you can really compute the value of these pictures. And sometimes the pictures are really just expressions in A, B, and C, and sometimes they still have some things which haven't been fixed, if they have external lines. And let's do one more example to make sure that we're all happy. So now we're going to put a thick line in at the first spot and a thin line at the second spot, but then we're going to let them come out in the other way. Orientations. So now, well, let's be a little bit more clever. We're not going to just draw all the possible configurations. We actually kind of know what should happen if we look at the pictures there. So we know that this line, it cannot just stop. So here there's a line coming in, and we see that it cannot go out at the top, so we know it must turn right. So what happens is we get this line, and then it goes there, and then we already have this, we have this, and we have this. And we see that the only possibility for the horizontal edge is like that. So we get this picture, and that's the only contribution. We see two vertices of type C, so we have C squared. And finally, one last stupid example is if we have one thick edge coming in and everything else is thin like that, then you can easily see that the result is 0. It's a picture. There are no vertex configurations internally. The line has to go somewhere. You know, I can make it turn to the right, but it will come back eventually, and then it has to go up, but that's not allowed by this sort of boundary condition. So we can compute the value. So here are some simple examples. I hope that they illustrate all these graphical rules. Another little, well, let's say that's a little exercise. You can take this picture like that. So a horizontal periodic line and also a vertical periodic line. And then you can check that this is 2 times 8 must be. Oh, so easy one, but 0. And actually, thinking about this a little bit more carefully, so another exercise is convince yourself that if I'm going to draw the whole lattice like what I just erased, so I'm going to have, let's say, 3 horizontal lines periodically like this, and then maybe 4 or something vertical lines. Well, in general, this is supposed to be K and L, many of them. Well, in this case, all the lines are internal, right? In the middle, they're really clearly internal, and on the outside, they're internal because of the periodic boundary conditions in both directions. So what it means is, according to our summation convention, we are supposed to sum over all the possible values of the spins for all the possible edges. So in other words, what we're going to get is the sum of all the spin configurations, so let's just say configurations. And then for each of these configurations, I've completely colored all the possible edges. So the result is really something in terms of A, B, C. And so what you're going to get is precisely A to the NA, B to the number of B vertices, and C to the number of C vertices. In other words, this is a graphical representation of our partition function. So okay, so that's nice. So it means the graphical notation is good for something. We want to compute this, and at least now we can draw it. So that will be very useful for what comes. So I'm going to use this a lot in what follows. So are there any questions about this, or are we all happy with it?
I mean, why do you insist on putting this 0 weight? You could just put them, and then you have lines that go.
Well, you could, but if I want to compute stuff for the 6-vertex model, then the weights according to the 6-vertex model are 0. But of course, you can go to the 2 to the 4th vertex model. I mean, you could just allow for all possible weights around. I mean, if
you wanted to some 8 vertex.
Well, you could if you wanted, or you could. I mean, if you wanted to say, right? If you want to allow for this, you're going to get a model with lots of vertices. It's not going to be integrable, and but you can put it on the computer if you want. Do simulations of it, I guess, or compute it in other ways. But if we want a 6-vertex model, then the rule is that we're supposed to do a weighted counting of all the allowed configurations according to the 6-vertex model. And this rule makes sure that we only get allowed vertex configurations, right? Because my summation conventions say that every possible configuration is going to appear, because we're just going to sum over anything in the intermediate step, like we did here. We had to sum over this according to our summation convention. But I don't want it. This will not contribute for the 6-vertex model. It's not allowed. So weight 0. Right? It will have probability. The weight is an unnormalized probability, so it should have probability 0 of occurring if you accept it. Any other questions? Are we all happy? All right. Then let's keep that example, and let me erase this. Okay, so this was the end of the section 4.1 that I started last time. So now we go to section 4.2, which is a transfer matrix. So the strategy to understand this partition function will be to cut up this lattice into smaller pieces. So what we're going to do, and what it will give us eventually, so really the idea, is we're going to express the partition function Z in terms of linear algebra. Which of course is good. Then you can just put it in a computer and you can at least compute examples. And to do this, what we're going to do is we're going to cut up this lattice in some ways. So to do so, cut the lattice into slices horizontally. So horizontal slices. If I want linear algebra, then of course I have to introduce some vector spaces because we're going to get matrices acting on these vector spaces. So for each edge, we're going to associate. So my edges look like this. For each of them, this is meant to be an so edge, and then we associate. This is not meant to be an edge. C2, so some two-dimensional vector space. And to the local degrees of freedom on the edge. So I have two possibilities now. I have either thin or thick. I'm going to associate a basis vector here, which I will call plus for this guy and minus for that guy. Note that this is precisely matching the orange. These are really the orange signs, pluses and the minuses. Okay, so this is just the basis, standard basis for that vector space. So in other words, what we're doing is we're just, because we want to do something in terms of linear algebra, we just say, let's make a vector space whose basis is labeled by the possible states by our possible local degrees of freedom. So then, if I have lots of horizontal, vertical lines like this, L of them, then to this I'm going to associate, well, we can think about the possible bases. You can have either dotted or thick lines for any of them. So I'm going to get a big vector space, which is C2 L-fold tensor product. And for instance, if we have dotted lines going up everywhere, then this corresponds to the basis vector plus, plus, plus in there, etc. Right, so for all possible configurations on my L, so what I'm doing kind of is I'm looking at a little piece somewhere in the lattice, like this. And I associate some big vector space to it with all possible degrees of freedom on those edges, spanning the vector, well, formally spanning the vector space. Okay, so now let's define this transfer matrix. So graphically, I can just define it by saying that C, which is my transfer matrix, is a horizontal periodic boundary condition thing, and then lots of vertical lines. So here I have L lines, and I have one horizontally. And so this picture, I claim, defines an operator. So we can view this as an operator or a matrix, which goes from, well, there's a C2 to the L at the bottom, associated to all of these lines here. And then it goes to C2 to the 10 power L, associated to all the possible configurations at the top. Right? So this, I can think of this as a matrix transferring a configuration here to some linear combination of configurations at the top. That's why it's called a transfer. And okay, this may look a little bit abstract, so let's make it very explicit. So we can just easily compute its matrix elements. So if I fix my pluses and minus signs on the top and the bottom here, then what I'm going to compute is, well, I get my S's are the pluses and minuses, so I have S1 prime up to SL prime, then the transfer matrix, and then S1 up to SL. In terms of this fixture, what does it mean? Well, this here, then I have all my edges, like before, and then here I have S1 at the bottom up to SL, and S1 prime up to SL prime at the top. And how is this so fundamentally different from this here? Well, here we had some kind of external edges from the bottom to the top. Whereas here we fix the spins everywhere because we fix the spins on the edges that were external, and everything else is internal, so there's a sum over it. So everything is a complete spin configuration. So what we're going to get is we're going to get lots of configurations all added up together. So what this is so we can note the result is a polynomial in A, B, and C. And it has the total degree L, because there are L vertices. So I can have L, A's, B's, and C's all together. And they're going to be at most 2 to the L terms, because I have sum over all these L internal horizontal edges. As we will see, luckily, actually, it is much less than this 2 to the L. So it will actually not be so bad. But before we get there, let's see why this transfer matrix is useful. Well, okay, maybe I should also say, because here I say you can view it as such an operator, so let me actually write the corresponding expression. So if we take a spin configuration and we act on it with the transfer matrix, like this, then of course we're going to get a linear combination of all the possible S prime 1 up to S prime L plus or minus. Then we're going to get S prime, T, S, and then the vector S prime. Right? So this is the operator acting on a vector with lots of matrix coefficients, giving a linear combination of all the possible output vectors. And what you see is that these entries that we can draw graphically like that, they basically give the likelihood, or more precisely the weight, of some configuration S prime occurring on top, one row above a given configuration S. That's what it does here, right? It sends this to a weighted combination of everything that can occur at the top with its sort of relative probabilities assigned there. So that is precisely what I mean by this statement there. All right. So now let's think of, here we had so we started with no rows of the lattice, then we assigned to that a vector space, then we looked at one row of the lattice. That's this part here, including the boundary conditions. That's our transfer matrix. So let's get a little bit bigger and go consider 2 rows of the lattice. So let's draw the picture first. So we have 2 of these rows. Then we have some number of edges. And let's again fix the spins. S1 SL horizontally and S1 prime SL prime from the bottom to the top. Actually, let's call it S double prime. So of course here there are lots of internal edges, so we're going to get a sum over lots of things. But let me focus on one part of these sums. Namely, we're going to get a sum over all the possible spin configurations on these vertical edges in between. So this is a sum over S1 prime dot 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 SL prime equals plus or minus 1. And then I have the same picture twice on top of each other, but now with a little bit of space in between. At the bottom I have S1 up to SL, then in the middle I have S1 prime up to SL prime, and then at the top I have S1 double prime up to SL double prime. Right, this is our graphical rule, the summation rule, which was our rule number 4. And also the periodic boundary conditions, by the way. Anyway. Oh no, not the periodic boundary conditions, this was just... Okay, so now this is nice, because here we see these pictures are precisely the pictures that we already looked at just here. So we know what this is. So let's write it. It's a sum over all the possible S primes. And then we have a matrix element. Well, we have this guy here, which is S double prime, P, S prime, and then S prime, P, S. Right? Because this is, I'm just identifying that picture and using this formula where I'm just writing S underlined like here. Okay, but this is nice because now we recognize that here we have the sum over S prime, and then we have the cat and the brow. So this is just the identity. In other words, what I'm going to get here is a sum, the brow of S double prime, and then T times T, so T squared, and then S. Like this. So we see that 2 rows corresponds to the matrix element of T squared if I fix the spins on the external edges. All right, so that's pretty good. Now let's think about the whole partition function. This whole picture here. Well, what is it? Okay. Let me do somewhat illegally. So this whole picture, which I'm allowed to assign values to. So what is this? Our partition function. Well, it's a sum over all the s's, and then I have this picture where I have lots of lines on top of each other, so k of them. So now I'm using the rule for our periodic boundary conditions, rule number 5, but not in the horizontal, but in the vertical direction. So here's S1, dot, 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 SL. And at the top, the same as 1, dot, 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 SL. But we've just learned how to interpret this picture. Here we have 2 lines on top of each other with the matrix element of T squared. So of course this is going to be the sum over all s's, and then the matrix element of T to the k. But now compared to SS. So you see that this is the sum over all the diagonal matrix entries of this. In other words, this is the trace of T to the k. Okay, so this is what I meant by express partition function via linear algebra, because here we have the partition function, which we could draw, and the drawing helped us to kind of easily make sense of all the multiplications and whatever happens, and we see that in the end, we can express this as the trace of some power of an operator. So we have a nice, so this is kind of good, because now you only need to tell your favorite computer program how to compute a partition function, and then you can just take some power and take the trace, and you know, the transfer matrix, and then you can compute from it the partition function. Okay. Maybe I should try to keep the graphical road reference. I would like to keep it. I think this will have to go. There are just a few remarks. So let's do an, well, there's an exercise. I think I used abbreviation for exercise as opposed to example. So it consists of a few things. So first, what you should do is use the arrow picture, by which I meant these little red lines, little red arrows on the edges. So, you know, they're all equivalent, but some pictures are more useful for certain computations and others are more useful for others. So I like these lines. I think they're much easier to see what's going on with lines that just have to follow stuff. But for this, the arrow picture is better. To check how the vertex weighs. And now let's remove our zero field assumption. So let's actually call the top there A plus and the bottom A minus, B plus, B minus, C plus, C minus, like that. So then at the moment take all the vertex weight A plus minus B plus minus C plus minus. And how they change under, well, reflections, either vertically, let me just indicate it like this, or and reflection like that. Or if we flip it top to bottom, or if we flip left to right, look at what happens to these pictures and which vertex weights stay the same, which ones become are mapped to each other, and so on. And the next thing is use the graphical notation to check. And now we go back to the zero field case, or the zero field case. A plus minus are both equal to A, etc. So here it was useful to keep them all separate so that you can see more clearly which vertices are precisely related to each other. But now we're going back to the problem that we're really interested in. And then you can check that the transfer matrix, if you take its transpose, is the same. so that this matrix is symmetric. Okay. Of course, if a matrix is symmetric precisely when its entries are related by, S prime T S is the same as S T S prime, and then you have pictures for both of them. And you can think about how everything changes and use the first part. And then finally, check that if you complex conjugate, which I will denote by a star, transfer matrix, then it's the same. So the transfer matrix has real entries. This is very easy. It just uses kind of a very basic physical assumption about these ABCD or ABC. If we have a real symmetric matrix, then it means that it has real eigenvalues. So let's denote them by lambda 1, and we can just order them decreasingly. Lambda 2, and so on. Now, if it is true that lambda 1 is larger than lambda 2, so there's some sort of a gap, and then some other stuff happens, then what you see is that Z was the trace of the kth power of the transfer matrix. So it's the sum of the kth powers of the eigenvalues. Lambda 1 to the k, lambda 2 to the k, plus dot plus dot, which is, well, let's first write lambda 1, then we get the 1 plus, and then we get lambda 2 over lambda 1 to the k plus dot 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 dot. But if there exists a gap, then this ratio there is smaller than 1, and now if k is very large, then this becomes smaller and smaller and smaller. So this goes to 0 if we let k go to infinity, which is something that you would want to do. You want to compute this partition function really not just for finite k and L, but thermodynamically. And so what you see is that actually the dominant eigenvalue, if this gap is big enough, or if, of course there can be many more contributions if we if we make L large as well, there will be many terms. So whether or not they still contribute a little bit to this or not depends on the details. But you see that the leading eigenvalues, the first few eigenvalues of the transfer matrix, give basically all information about the partition function. So the goal is, rather than computing Z, we just need to diagonalize transfer matrix. So our new goal, diagonalize the transfer matrix. And so people can really do this and use this to compute the limits both for L going to infinity and K going to infinity, and then you take the logarithm and you can really compute the free energy and even finite size corrections to it using this transfer matrix. And I should mention that this transfer matrix was famously used by Onsager in 44 to do similar things for the two-dimensional Ising model. So it was the idea was already around for a while when six-vertex model really became popular. Very good. So now we're interested in the transfer matrix. Am I allowed to erase this, or are you still this part over there? Let me slowly do it. Okay. So since we like the transfer matrix, let's actually see how well we understand it. So let's do a few little examples. Okay, so if L is 1, just to make sure that we understand everything. So the transfer matrix in this case is a 2 by 2 matrix. And so let's draw 2 by 2 matrix. And we have the input vectors there and the output vectors there. And we order them like this and like this. And we have this and this. Right? So in other words, I can graphically write the entries here. This one is this one is this entry here, this, and this entry here. That little picture. These pictures have horizontal periodic boundary conditions and externally values at the external edges, so they're just polynomials in A, B, and C. And you can check that here this is not possible, so the off-diagonal terms actually vanish, whereas the diagonal terms have two contributions, namely A or B for each of them. So it's just A plus B times the 2 by 2 identity matrix. So in small, the point is in small examples, you can really use this graphical notation to compute the partition function, the transfer matrix entry by entry. Okay, so let's say a little exercise. Repeat this story for now length 2. So check, I'll tell you what the result is. But in this case, the transfer matrix, hopefully I did my computations correctly, is A squared plus B squared. Then to the right, then we get a 2 by 2 non-zero block with 2ab c squared, and it's symmetric, like that. And then finally, A squared plus B squared. And all the remaining entries are 0. So it's a 4 by 4 matrix with only 6 non-zero entries. And we note that it's block diagonal. Now this block diagonality is not a coincidence. So note from it, so here it was diagonal, but it was just because the example was so small that we didn't really see that secretly it's block diagonal. But what we noticed is that the ice rule, which remember was the rule that really told us that only these 6 vertices are allowed. So for instance, in terms of the arrows, it meant that there are equally number of arrows pointing in as arrows pointing out. It was the electric neutrality of the ice model. Together with periodic boundary conditions, implies that the transfer matrix conserves the number of these thick lines. If there are 4 thick lines coming in, then there will be at the bottom, then there will be 4 thick lines going out at the top. And that is what is block diagonality.
Jules, could you write the choice of basis?
Right. So it's just right. Yeah, of course. So well, I mean, like this, it's the standard basis for if you have a tensor product of vector spaces. So this, and this, both for the incoming and for the outgoing vector space.
Okay.
Right. So I will just order. I have my basis for my 2-dimensional space, so I will just extend it in the usual way. Note that the convenient way sometimes to kind of think about this is you identify these dotted lines by zeros and these thick lines by ones, and then you just have binary strings. So you can just, it gives an enumeration of possible 2 to the L basis vectors in the vector space. Okay, so it conserves this number of thick lines. So let's do a very simple example. Let's look at the case where the number of these thick lines is 0. So what it means is that we have our transfer matrix with only dotted lines around it, like this. Now we have to sum over all internal edges. So let's first do it here, let's say. So this is either empty or a thick line. If it is empty, then there are 2 empty lines coming in, so there must be 2 empty lines going out, and so on. So what you get is that all the lines are like this. Or it was thick, and then it has to go out all the way at the other side. So even though the transfer matrix, it kind of moves you from one to the other, something happens kind of internally in this horizontal line, and there could be a line there even if you didn't kind of see any lines from the outside. And this is of course related to the fact that this entry here has 2 terms like that. So in fact, I'm already telling you the answer of part of this exercise here. This is in general A to the L and B to the L. So we can compute that 1,1 entry of the transfer matrix for any length very easily. And that's 2. Okay, good. I guess I have a little bit more time. if I want to continue. Maybe we can just take a little break now and then continue in 10 minutes or whatever.
Okay.
Are there any questions? Of course, I mean, well, people online should also, but any questions? Mm-hmm.
Just suppose that in the don't apply periodic conditions.
Yes.
Then it becomes a nice, yeah.
No, well, no, not necessarily, right. So here we have a partition function. For us, we chose boundary conditions, but indeed you can choose other boundary conditions. So let me just draw some examples of other partition functions that one might to compute. So this one that we have here, okay, so let me draw them a little bit more small. So we have this one, which let me call it, it's the Z on the torus, which looks like this, and then like this, okay?
On the cylinder, it's the same thing.
Still, well, not, I mean, we have it periodic in both directions.
Okay, but if it's not periodic on the vertical, it's okay because it's just a matrix element.
You could do it, but then it's really a power of transfer matrices that you're computing. So, right. So,
now if you have anything fixed on the boundary.
right. So now we're going to all the possible fixed boundary conditions on the X. So this is also possible. So for instance, what you could do is, so let's first draw some lattice like this. So we can do lots of possibilities on the external edges. So one possibility is we just, so let's say we have S here and S prime here, and I don't know, actually let's call this S prime, S double prime, S triple prime. What we can do is we can just sum over all the possible external spins. Okay, so this is called free boundary conditions. This case is kind of horrible. There are many contributions. So partition function really contains many terms, but it's a partition function that one might want to compute. Another case that you could do, well, we can be a little bit more restrictive, so we can only sum over part of all the possible configurations that I had here. So let's do some examples. So for instance, I have my lattice like this, and let's say that I just fix everybody to be this empty line. So here, well, there are no thick lines coming in, there are no thick lines going out. They can't just appear out of nowhere. So this partition function, actually everybody is just, all the lines are dotted. So what happens is that this is just A to the K times L. So this is a really boring case. This is sort of a maximally polarized, completely polarized, and completely fixed configuration. So this partition function is very boring. So actually, and this was because of this line conservation, because of the ice rule. So you see that for the six vertex model, the ice rule is really extremely restrictive, because normally we kind of say, oh, we fix some boundary conditions and it doesn't really matter, so let's take periodic or whatever. But here we see that it really matters a lot. Of course, this case is translational invariant, whereas these are not. So there's some real difference between them. But you know, here we have a huge sum, and here we have a single monomial. So it's really huge difference. Some other examples. Well, of course, what I could have done is I could have instead taken this to be a thick line here, and I could take these to be thick lines. Then instead you just get B decay L. So it's another very boring case. Okay, so now let's do some more interesting cases. So one case that people really like is the following. We start with dotted at the bottom, and we start, actually I'd rather take a square lattice in this case, so K equal to L. And I start with all empty here, and I put all thick lines here. But somehow the idea is that you start with kind of no lines, and then you inject one by one line, and I force these lines to exit at the top, because there it was boring. So let's instead do it like this. This case is called the domain wall partition function, like that. And the reason is somehow that here, you know, we have our plus spins all the way like that, and then here we have minus spins all the way like that. So somehow here and here we have two domains, a plus domain and a minus domain, and there's some domain. So it's not a very good name, but it's the name. So this case is actually super nice. Some of these boundary conditions are integrable, others are not. So this one is integrable, as we will see. This one is not, I don't think. This one is extremely simple, so okay. This one is also integrable, and this is really nice. So the difference is that here we will have to use beta ansatz, this one you can compute in closed form really neatly. So this is very, very nice. It's also related to alternating sign matrices and was used for a very nice proof by Kuperberg of the alternating sign matrix conjecture. So this is extremely, it's also related to dominant tilings of the Aztec diamond at a particular case. So this is a really nice combinatorial case. And then there are lots of other cases that you could consider. So for instance, something that one could try, it really doesn't matter if we have equal number of lines in this case. So what
one? There is more than one configuration of this one?
here? Okay, little exercise. Do it for LS2 and check. No, there are lots of them.
It seems if the first line doesn't exist in the first column, then the other will never be able to exist.
So exercise, compute for LS2 and LS3.
Yeah, I forgot they could cross.
There's actually an extremely nice formula, like a factorized, like in terms of some simple factorials for the number of configurations.
Yeah.
So there are some numbers here. So what you could also do here is, so you see the reasons that this is sort of good, the equal number of lines coming in and out, of course, otherwise the result would be empty. Where it means coming in means at the left and the bottom, and going out means at the top and the right. But this was too boring because it's kind of the input was too polarized in some sense. So what you could do is you could try doing something like this. So you kind of alternate this. It's kind of not unreasonable. And this case is not integrable. It's too difficult. So really, there are all sorts of cases, and you know, we're going to use integrability, but the boundary conditions may or may not be compatible with integrability, and only in some special cases they are. But these are all valid partition functions that you can compute. And the point is that none of them have external edges anymore. In all of the cases, they're either all internal or we summed over, we fixed the value of the external edges. So they're all kind of invariants, and so they're good partition functions. Polynomials in A, B, C of degree k times L, with many, many, many steps in general. Okay, it's a long answer, but by the way, Philippe, who just entered, he is like a super expert on this domain wall partition function stuff, for instance, and all these exotic models. All right, so we will continue. Right. So what I did so far is I introduced a lot of kind of pictures, and I showed you that you can use these pictures to compute stuff. And I think this is very good and the most useful thing, really. So the rest of today, what I want to do is I will sort of outline how we can use the coordinate beta ansatz to actually diagonalize the transfer matrix. And then we will see, this will have some very cool, so I will not say so much about how to really do it in detail, but rather what the results are and what this means, because this is very important. And so this is due to Lieb, who did it first for, remember, this special case, which is called square eyes, where we have A equal to B equal to C. So you just count the number of configurations. Then there was this potassium dihydrogen phosphate or whatever, and then there's this F model, which I forget. So he did this, and then Sutherland, not much later, did this for the six vertex model in general. So what they did is they actually diagonalized the transfer matrix using the coordinate basic ansatz, using the coordinate data, sorry, ansatz. But this is quite remarkable. And to be honest, I don't really know how Lieb realized it the first time, but I think it's around 66, 67, so it's very close to the time of Yang and Yang. So maybe he kind of learned about the beta ansatz and then thought, okay, let's beta ansatz solve something, and somehow happened to find good models to attack in this way. I actually don't know how it works. So, but certainly once he wrote a few papers, so this is physically it was quite nice because this model has an infinite order phase transition, for instance, and so he found some really cool results. But then Sutherland realized, okay, actually we can just do this for arbitrary A, B, C, and basically do the same. So let me try to motivate it as well as I can. So let's compare the properties of the XXZ Hamiltonian, and we're going to compare it with the transfer matrix. to kind of see what did we use last time in the beta ansatz and what do we have this or do we not have this in the current case. So firstly, which was super important, is that the spin in the z direction was conserved for the xxz spin chain. So what this meant is that the number of down spins, this is now the down spins on the spin chain side, was conserved. And this is really essential for the coordinate beta ansatz. Because this allowed us to fix the number of down spins, and then we could write the beta ansatz in the first place. So if we don't have this, then it would be very problematic. So what we can do, of course, is in our case, we can identify on the 6 vertex side, we have this configuration, the empty one, and we have the thick configuration. And we will, so remember that to the empty case, we assigned the vector plus, and to the thick line, we assigned the vector down. So this was still the 6 vertex, but now in the vector space. What we're going to say is we're going to just say that this is equal to spin up for xxz, vector space, and this is spin down, like that. And this allows us, so this is good, and it allows us to use the coordinate basis. And here we have to note, I erased it, but I mentioned before the break that we saw this, that the transfer matrix in the small example is block diagonal, and I noticed that it preserved the number of down of these thick lines. So that is precisely this, the corresponding property of the SZ, of the spin Z symmetry. Maybe I should say for the transfer matrix, this is okay because of the ith rule, which says that these thick lines have to continue in some way, either straight or kind of bending, so that they generally go from the left and bottom to the top and right. And then together with the horizontal periodic boundary conditions. Because this means that if the thick lines turns to the right and just went off to the right, then they will eventually come back from the left and they have to turn back up at some point. So if they come in from the bottom at some point, they will have to come out at the top somewhere. And we saw this in the examples that I computed. So this is good. Remember that I denoted the coordinate basis by this L with a double kind of arrow at the time, which was the vector which has down spin sitting at location L1, right? So let's say this is down spins, which is now equal to our minuses at L1 up to Lm. Okay, so that's good. So the crucial property is definitely there. Then the next thing that we use is this translational invariant of the xxz Hamiltonian. So there was this translation operator, G, which commuted with the Hamiltonian. Okay, so what did we learn from this? Well, one thing is we had momentum conservation. But this is not really essential, so I'm putting it between in parentheses. But it was useful for efficient bookkeeping, right? So remember, we extended the coordinate basis a little bit, and it was quite useful to kind of simplify and order our computation. So maybe I should also say this: it was kind of useful for bookkeeping. And then moreover, we have these periodic boundary conditions, which is closely related to it, because we can express this, for instance, as saying that the Elf power of this translation operator is the identity. We shift everybody completely around so that nothing happens. And in terms of the coordinate basis, this meant that L1 dot dot Lm is equal to L2 dot dot Lm comma L1 plus the length. So we identified these two vectors. And this led us to our beta ansatz equation. And last time I tried to convince you with some examples that this is really crucial because this fixes the values of those parameters in the beta ansatz. And with a lot of extra work, one can nowadays prove that this really gives all the possible eigenvectors. So this is really a crucial part of it. But this is also essential, at least for IPhT, for this thing to work. So how about that? Well, little exercise. Check that. I think I erased it in the meanwhile, so let me draw it again. The transfer matrix, which is this picture, commutes with this translation operator, which for me I can draw like this. So there's lines and they move one to the, well, I made it the left shift operator. So like this, and then periodically we come back like that. So it's a periodic shift to the left by one. So this is a good way to draw shifts operator. And you can do this nicely graphically, for instance, by computing a commutator graphically and taking matrix entries, and you can really see that everything works nicely. But of course, it's not so surprising. But this is good. So for transfer matrix, this is okay by following exercise. So periodic boundary conditions and translation invariance are good with the same translation. And then the third property that we use is that the spin chain was nearest neighbor. So XYZ is nearest neighbor. So what this meant is that the difference equation, remember we took some components of the eigenvalue equation this gave a difference equation for the wave function, and because of the nearest neighbor interactions, this one is rather simple. And in particular, it led us to eigenvalues that are quite simple. Well, so this epsilon for one particle, this was twice delta minus the cosine of p, and let's say this was simple. Okay, so nice, but it doesn't sound essential, and indeed it's not. So this is not. So for the transfer matrix, so here's another exercise. So I've done a lot of examples for very small length, but now let's, well, you will convince yourself that you can actually do the computations graphically also for arbitrary length. So what we're going to check is the following, or what you're going to check is that if you take, now I use the coordinate basis because why not? The transfer matrix, if we take its entries in the coordinate basis, like this, then, well, the result is pretty simple. So remember, in general, there were 2 to the length many terms, but in the examples, actually, it was very limited, the amount of terms that appeared. And in fact, you can easily characterize it. So there are 2 terms if L is equal to L prime. So if the ingoing and the outgoing spin configurations are precisely equal, then the transfer matrix has 2 ways of doing this. Next, it has only 1 term if, well, L and L prime are interlacing. So if they interlace, which means the following: either all Lm primes are less than the, sorry, well, it doesn't matter. All Lm primes are less than Lm for all m, or the other way around. And so here I inequalities, but not straight. So n, at least one of them is straight. One strict equality. Okay, so graphically what it means is that if we have some configuration like this, oh, actually I should say a little bit more. They are supposed to interlace, so I'm supposed to have something like this. So either lm prime is smaller, well, so lm is either in between lm prime and lm prime plus 1, or the other way around. So what this means is that if I start with a configuration like this, then either these can all kind of stay maybe at the same place, or they can move one to the right. So for instance, this one could go there, and then this one could go anywhere here. So let's say there, and then this one might be going there. So this is interlacing. But what can never happen is if I have this, this, like this, and then it goes like this and this. That is not okay, right? So basically, one has to go out before the next one comes in, or at least at the latest at the same time, kind of, as the next one comes in. And this is kind of clear also from the vertex.
But should, of course, the one you draw is possible.
This one here?
Yeah. I mean, it's not interlacing, but it has a non-zero.
How does it work? Well, let's try.
No.
Let's see. So here, this is supposed to be all like this, right? So how does it work? So okay, so this line here, well, let me start here. This line here, it has to go, it cannot go to the top, so it must go to the right. That's that. Then here, this dotted line must go to here. But now we have two dotted lines coming in and one thick line going out. So this is zero weight, and I mean it has zero statistical weight.
So these are only non-zero metrics.
Exactly. So this, the result, so that's the last part here. It is 0 else. So this is extremely nice. So this transfer matrix a priori contains like many terms, and it's very complicated. But in fact, the two terms only occur in the case that the incoming and the outgoing vector are easy, super easy to compute. Then there's only one term in the kind of complicated case, but you know you can draw it and you can just really write down the formula. It's not so bad. And then it's 0 any other time. So it's super nice. So it really gives a lot of control. So even though this transfer matrix may have started out as looking very weird and abstract or whatever, it's really a very simple matrix with entries that are mostly 0 and otherwise contain a monomial or maybe a sum of two monomials on the diagonal. So very nice and easy.
What do you mean by not so for T? I thought you meant it's not so simple.
Right, well, it is simple, but it's not nearest neighbor.
Oh, okay.
Right? So what can happen here, I hope that my example here, right, so here, for instance, this would go here.
Yeah.
So you kind of think of this spin, it kind of hops there. This guy hops to the neighbor, but this one hops all the way over there.
Yeah.
So it is not nearest neighbor. So not so for T, okay, but still simple. Simple enough, let's say. Very good, yeah. Okay, so not nearest neighbor, but at least not super hard, so maybe there's a hope to do the coordinate beta. I think I want to skip. I won't really draw much anymore, but I think this is my favorite part of today's lecture, so I will just want to keep it up there. I will slowly erase this. If you haven't finished copying yet, then just tell me to wait. So we want to find vectors that take psi tilde, which are eigenvectors of T, with eigenvalue capital lambda. So I'm going to do this in a bit less detail than I did last time, but I'll tell you how to do it. And the point, of course, is that we're going through all this painful coordinate beta ansatz, so that next time, today we'll learn something really cool, and then next time we'll be able to use what we learn at the end of today, or maybe early next time, by doing something much better, much faster. So it's okay if you don't really follow how it's going to work, but what is important is the result. So the strategy is as follows. This is what Lieb and Sutherland did. Okay, so we have this eigenvalue equation. So first, of course, we're going to project it onto some coordinate basis vector in some number of thick line sectors. Then we get an equation which is just in terms of wave functions. And we're going to use the coordinate data ansatz. So we're going to say that this wave function is our good old friend, I'll now call it psi tilde. Remember, there was a parameter p, which I will now call p tilde, and it depends on L. Sum over all the permutations of the thick lines. Some coefficients, let's say a tilde, depending on the permutation and depending on our parameters. And then these plane waves with p tildes now and permuted like before. So just to completely emphasize, these are now the coordinates of these thick lines. But we'll just do the same. We will associate to each thick line kind of a quasi-momentum parameter, p tilde. Associate, we call it the quasi-momentum. And now it's called p tilde. So we apply this, we plug in the coordinate data ansatz. On the right, of course, the result is just that, but on the left, you have to compute something. So the exercise is super useful because it tells you that there are not too many things on the left-hand side. And those things that are left, we're going to combine the terms using geometric sums. Oh, and by the way, I guess I should really say that as part of this exercise, you should also actually compute. That's really the first part is the hardest work. Once you've convinced yourself that this is true, then it's not so hard to compute the actual entries. So you will use them in the left-hand side, and then you'll get some geometric sums, which you can perform. So this is how to get kind of an analog of the difference equation.
So we should have to instead of what?
Of this EG. Right, so I'm applying L to this here, so I get the left and the right-hand side. So on this side here, I've stuff with transfer matrix, so lots of these entries like there. And then I use some sum to combine terms in there. So to solve it, there are three, there are some different cases to consider. Usually the first parts, they're called the wanted terms. So these are those that are some coefficient times one of these plane waves. If this coefficient is independent of L. Okay, so for some permutation, you will look at this coefficient, and you will see that such wanted terms, well, for this equation to satisfy, to hold at the level of the coefficients of these exponentials, you're going to find the eigenvalue up. And everything else is not wanted, right? So the good thing is here, this is on the left-hand side. On the right-hand side, we have all these kind of things, but on the left-hand side, we've generated some extra stuff that we don't really want. So these coefficients, we're going to just equate, right? So independent of this, and these are coefficients on the left-hand side, and you're going to equate it with the coefficients on the right-hand side, and then you're going to find the energies. But on the left-hand side, there's extra stuff, which we don't like. It's not of the right form. It's not of the beta ansatz form. So this better vanishes. It's called unwanted terms, and there are two types of them. So this is the rest. This was of coordinate beta ansatz form, let's say. So the rest, well, what can we have? There are those that are sometimes called internal unwanted terms. And this means they contain things of the form e to the I, some p n tilde plus p m tilde times L, or the other way around, e to the IPM tilde plus PM tilde LM. So what you see that happens here is that the nth and the mth thick line are sitting at the same place. But this is not okay. They're not supposed to sit on top of each other. So in this case, we ask for these coefficients not cancel, because these exponents are not good. And what this will give us is these coefficients of the beta ansatz A tilde W as a function of P tilde up to normalization. Of course, I will tell you, so this is the results. You will find this. I will tell you what the answer actually is in a moment. Finally, there are the boundary terms. Which is really all the crap that's left over that we don't want. And what we will also, they must also, their coefficients must also cancel. And this gives beta ansatz equations. Some beta ansatz equations for the P tildes. So this is how you structure the computation. And I should emphasize that for the XXZ spin chain, we had three different conditions as well. We had one condition which was kind of like the wave equation. It was the good part, the kind of the wave function, and it gave us the eigenvalue, and it was very simple. Then the next part, and we simplified this a little bit. For the next part, we had those things which I called the kind of like the bounce equation, which described, which kind of said basically that particles are not supposed to, the downspins are not supposed to sit on top of each other. This is the analog of it for the 6-vertex model, and like there, it gives the coefficients in the wave, in the beta wave function, in this coordinate-based ansatz. And then finally, there are some extra terms that, if you think about it a bit more carefully, have to do with the periodic boundary conditions here. And their coefficients must cancel, which is beta ansatz equation. So the structure of which kind of part of the equation to give which output is exactly the same as it was for the XXZ spin chain. But the details are harder, you know, I mean, you have to, everything was a bit more complicated. It can be done. Okay, so maybe an exercise. Actually do this. Well, for M is 1, for M is 2, and since we have, you know, some of the exercises came in the level normal, challenging, masochist. So 3 is the masochist level. Quite useful. But let me tell you what the answers are going to be. Of course, it's very useful to do it. You should really do it for general M. But if you can do it for MS3, then in fact, at that point, it would have been more efficient actually to do it for general M. You have to think a little bit better about your bookkeeping, but all the complications appear at MS3. Now, in integrability, it's kind of like MS0 is trivial, MS1 is also kind of too easy, MS2 is getting a bit more interesting, MS3 is hard, and then that's kind of like 3 and infinity is the same. It doesn't matter anymore. You just do general. So we count with the one extra number compared to the 0, 1, infinity. Well, two more extra numbers here. All right. So the results are as follows. So firstly, this eigenvalue, lambda p tilde. Well, it's just some polynomial in the vertex weights. And we can write it down explicitly. Of course, it also depends on these p tildes. So a to the L, product over all the m down thick lines, and then a ratio b times e to the I p m a minus b plus c squared divided by a times the same e to the I p m a minus b. And then there's the b to the L, similar product from 1 to big M, a. Now, so not b, but a times the same ratio, e to the I p m a minus b. Now it's minus c squared rather than plus c squared. And then you get over b. And then the same e to the I p m a minus b. So the structure is a bit different from XXZ. Remember, we got this nice functionally additive result where the M particle energy was the contribution of all the separate particles. Here, it's not that simple, but it's actually kind of nice. It's not quite factorized, but there are two terms, and those are explicitly factorized in fairly simple pieces. So, it could have been much worse, I think. You can also see, so for instance, here the denominator has degree, well, here's a degree one vertex. Here, this is also each contain one vertex. So this is degree 2, and the numerator is also degree 2. So we see that this is degree L polynomial in total. Well, whether it's polynomial or not is, of course, a question. But it looks like it should be degree L, and this is also degree L, which is good because the transfer matrix is also, its entries were also degree L. And so the answer is really rather not too bad. But then, this ratio, remember, in the spin chain, we can't really compute the normalization through this thing, but we can compare the coefficients of any permutation with the coefficient of the identity, let's say. And last time we found something, and we also found beta ansatz equations. And the extremely remarkable thing is that they are, as for xxz, just with p, which we had there, replaced by p tilde that we have here, and the delta that we had there. I should write this a bit bigger. Delta, well, I can say here, delta is going to be replaced by delta tilde of ABC, where delta tilde of ABC is the ratio a squared plus b squared minus c squared divided by 2ab. So this is really an extremely important result. And really everything else that I'm going to finish is kind of develop the consequences of this with a little bit of extra thinking here and there. But this is really the key of why, and actually the reason why in these lectures I think it's useful to go through the coordinate data. So some people, actually many people don't do this. They start from where we will go next week, actually. But then you kind of, you have a big framework, and then maybe it will not make sense so much. And here, I think this is nice. This is how it historically went. You really see that somehow you try the same strategy and you get some extremely cool results which show that these two models are closely related because almost the same wave functions, and with the right identifications, really the exact same wave functions show up to diagonalize both of these operators, the Hamiltonian and the transfer matrix. So it's really very, very. So given completeness, which I mentioned last time a bit. So remember, this is the statement that actually all the vectors are of coordinate beta ansatz form, all the eigenvectors. So you can, firstly, you can really count the number of solutions of this beta ansatz equation, and you can check that there are 2 to the L of them, if you do the counting correctly, and moreover, that all of the corresponding vectors are linearly independent, non-zero, so they really span the Hilbert space. That's the problem of completeness. It can be proven. This is, as I mentioned last time, is from 2009, so it's very recent result. But assuming that this is true, this means, or assuming, knowing that this is true, this means that firstly the transfer matrix, which depends on A, B, and C, commutes with the delta, the XXZ Hamiltonian, if delta tilde of ABC is equal to delta. Because they have joint eigenvectors. So notice the eigenvalues, they're very different from what we did before. But the eigenvectors, they depend on these ratios and on the values of the parameters. And both of these can be completely identified. So the transfer matrix of the 6-vertex model has exactly the same eigenvectors as the Hamiltonian of the XXZ spin chain, if only the vertex weights are related to the parameter delta of the XXZ spin chain.
Usually this was noted by Liebnitzfeld, or?
No, I can't really, well, no, I think this is Sutherland, probably. I'm not 100% sure, but
at that time it was.
Yeah, right. So this is due to Sutherland for XXZ, and then later, well, with the actual connection at the level of the operators. This is also, I think, it's due to Sutherland, and Baxter found it for X, Y, Z. It's vertex, I think. But my memory is not so good of those days. Moreover, what you see is that the transfer matrix with weights A, B, and C commutes with the transfer matrix with weights A prime, B prime, and C prime if they have the same delta tildes. So if delta A prime, B prime, C prime is equal to the delta tilde of ABC. So this is really a consequence of the results found by Lieb and Sutherland, together with the assumption that really we found all the possible eigenvectors. So this is also very important, but it's a consequence. I forgot one exclamation mark.
What I meant is that this was understood before the algebra.
Yeah, absolutely. Yeah, right. Yeah, totally. Yeah. And running a bit ahead to next time, I think it's so the way that I think one can and kind of should think about the algebraic beta ansatz is through the 6-vertex model, because then we can draw diagrams, we can really understand where stuff comes from, we can then do really nice and quick computations, and we get all these neat results. But you really kind of combine crucially that somehow these two models are really closely together, and this is the historical origin of those observations. So I think it's super useful to go through the pain of the coordinate beta ansatz, even at the level of an outline, to kind of understand where all that comes from. Okay, so let me really kind of unwind a little bit further what this means. So we have three vertices weights, A, B, and C, so 3 parameters. On the right-hand side, we only, for the XXZ spin chain, we only have a single parameter, delta. So let's try to understand a bit better how these models are related. So what we're going to note is that actually the 6-vertex model, it very weakly depends on all 3 parameters. It depends more crucially on only 2 parameters. Namely, if you rescale A, B, and C with a common rescaling, let's say R, which is non-zero, then, well, this ratio delta tilde is extremely important, but it's homogeneous, right? It has degree 2 in the numerator, degree 2 in the denominator, so it does not change. So the delta tilde fixed. Maybe I should also say that actually the beta ansatz equations. So remember, they contain these s of delta, which was something like -1 to the -2 delta e to the IP plus e to the IP. Oh, we don't see it here. Never mind. I don't have to remember this. So this is the crucial part. So delta tilde is fixed, and moreover, so go back to the 6-vertex model, it just rescales the partition function by, well, you just get the R for each vertex, the homogeneous polynomial of total degree KL. So it doesn't affect the thermodynamics. If you take the logarithm, it's just a constant, irrelevant for physical properties. And moreover, it just rescales the eigenvalue lambda. This was a degree L thing in the vertices, so this is also rescaled a little bit. So partition function and the eigenvalues of the transfer matrix depend on this because it's, you know, they can be normalized, but really the delta tilde doesn't change, and delta tilde is crucial for the connection to xz. So we're going to fix the ratio A, B, C. And we're going to fix this function delta tilde of A, B, and C to be equal to this value delta on xz. So this is fixed. So out of the 3 degrees of freedom A, B, and C, it leaves 1 degree of freedom if we fix this and we fix this with 2 constraints. It leaves 1 degree of freedom. So let's call it U. Well, let's parameterize it by, let's say U. So this is called the spectral parameter. And so I will just simplify my life a little bit, and I'll say that C of U is the C A of U and the B of U and the C of U at fixed ratio. Well, doesn't really matter, but let's fix it if it doesn't matter, and fixed value of delta tilde. So this transfer matrix now has 1 degree of freedom in there. And from our previous results, we see that the transfer matrix of this U commutes with H delta for all values of U at the fixed. Let me just repeat, delta tilde is equal to delta. That's really the crucial point. And maybe R fixed, but it doesn't matter so much. And moreover, the transfer matrix of U commutes with the transfer matrix of some other U prime, which has the same value of delta tilde. So this is also true for all U and U prime. In other words, we have a one parameter, namely parameterized by U, family, transfer matrices, that commute with the XXZ Hamiltonian, and they commute, well, and note, by the way, they also commute with the translation operator, so with everything that we know about XXZ, and moreover, among themselves. So this is the third consequence. I mean, consequence of the consequence. But this is also extremely important. So this is really often taken to be sort of, this is one definition of integrable systems, because what this says is that actually the XXZ spin chain, or as a given 6-vertex model, has lots of symmetries. So let me work that out in a little bit more detail to finish. I'm going to write the delta again because it's important. So delta tilde of A B C was A squared plus B squared minus C squared over 2AB. Okay, so let's assume there exists some analytic parameterization of of A, B, C by U at fixed delta tilde is equal to delta and some fixed scaling that we don't care about. Then what you can do can define, well, we can, let's say we can expand transfer matrix T of U as some power series Tk, what's a good letter? D, U to the D, or some, maybe D, depending on the precise parameterization, it might be like this, or maybe it's a series in U inverse, but it doesn't matter so much. It's going to expand as some series with whose modes, whose coefficients are just operators that no longer depend on this U. And then these, well, these TVs, they will all commute with H delta, and they will commute amongst each other, amongst themselves. So these are no longer depending on the free parameter U, but they're really just operators, just matrices with no free parameters anymore that commute with our XXZ Hamiltonian, and they commute amongst themselves. So this is really the construction of lots of symmetries for the XXZ spin chain that last time I kind of mentioned that the results of the coordinate beta answers suggest there should be, because these particles are kind of very polite and they interact very nicely with each other. They behave very well. Normally, one doesn't actually really do this. This expansion is not so good in terms of locality. So actually, what we usually do is we instead do an expansion of the logarithm of this thing. Just makes things look a little bit nicer. So what you can do is you can define HD to be the d, d to the d derivative at some fixed point u star. So here I expanded it infinity or 0 or something like this, but actually I can expand it whatever point I want. And then I want to expand the logarithm of the transfer matrix. It's better for locality properties. Operators that you get out of this are a bit more local. So let's define those. Then the same statement is that HD and H delta commute, and HD and HD prime also commute for all D and D prime. And these are really what one often takes to be the Hamiltonians, the higher Hamiltonians of the XYZ spin chain, this logarithm of the transfer matrix. And actually, I can choose any value of U star. But of course, some values are better than others. For actual computations and results, the results can look really nice or can look bad. So in some cases, it looks really good. So in other words, we found many commuting charges of H delta and also of some transfer matrix with some fixed value of the parameter. Well, or maybe rather I should say some transfer matrix with fixed weights A0, B0, C0. Right, so given a 6-vertex model with some weights A0, B0, C0, compute its value of delta tilde, then we have a one-parameter family of transfer matrices that all commute with it, and so we have lots of commuting transfer matrices, not just for the 6-vertex model, but for the XXZ, but also for the 6-vertex model. And they all come from the same, they all belong to the same family of lots of commuting operators. This, by the way, is actually called the beta algebra. So this big and usually, well, often maximal abelian subalgebra of all the operators on our Hilbert space. It's called the beta algebra, and the beta ansatz seeks to, that's why it's called the beta algebra. The beta ansatz wants to diagonalize them because they commute. So we can do this.
Is H delta part of the HDs?
So that is the question, and so that's where we will, that will be the starting point for next time. So let me just kind of draw a little sort of, as the very last bit, a little kind of overview. So we had our transfer matrix of A0, B0, and C0. Then we had our transfer matrix of any value of U, and then we had our XXZ spin chain, H delta. So what we saw is that these two, so H delta, well, it commutes with this stuff if we set D tilde equal or delta as our fixed value of delta tilde for this model here. Right, so this has some delta tilde. And here we can do the same. We have to set delta tilde to be the delta tilde of A0, B0, and C0. So then we get from either of these operators, we get a one-parameter family of commuting operators. Of course, here we can easily go back. We just take our U to be, well, we have to find an appropriate value of U tilde of U0, and then we will get back this family if we want to. At the same time, here we have lots of operators, so this gives lots of symmetries for both of these models. But your question is, how can we really directly kind of go back here? And that question will be the topic of next time. So that's what I want to say. Are there questions, comments?
What about algebraic independence of HD?
Right. So so what you want to do here, well, you know, but I mean, this is a technical question. The answer is going to be much more technical than the level of what I've been teaching about. But so what Muffin Sebastian do is actually the spin chains, the formalism that we'll look at next time, that allows you to kind of modify it, put lots of extra parameters to deform a little bit, and you can do it in a way that preserves all the essential algebraic stuff, but it lifts degeneracy. So you can break the spin Z, well, not the spin Z symmetry, but you can break, if you are delta as 1, you can include a little twist to break S plus S minus symmetry. You can include inhomogeneities to break translational variance. And so what you can do is you can make sure that all these eigenvectors, operators have a simple spectrum. So only one-dimensional eigenspaces. And then what you can do is you can count that, I mean, then that's where they do their counting. So they check that there are really 2 to the L many operators, that is maximal bigness of algebra as dimension 2 to the L. And so you really know that you find actually all the, with a simple spectrum, so you find all the eigenvalues for all the, you completely diagonalize everything. And so that's I think sort of roughly the idea. But you have to deform a little bit, and then actually what you see in doing this is that actually this Hamiltonian is in fact contained in that class. So what you can do is you can maybe take some sort of limit, so you can really show that everything works very well in almost all cases. In the precise sense that there may be some measure 0 values of the parameters where it's not okay, but I think it's almost always okay. And in particular for this actual case, that's really it works.
Yeah. Question: when a square plus b square equal to c square, you have zero anisotropy in the.
Yes, right. So this is our free fermion point.
That's and what about, is there something special in the six-vector model?
Well, the six-vertex model is also a free fermion model at that point. In fact.
But do you see some symmetry in the original model? I mean, XXX.
XXX is delta as 1, right?
Yes.
So XXX
One,
is
okay.
delta as 1. So we can actually look at this for a second. So XXX was delta as 1. So what do we get? We get 2AB. Well, 2AB is a squared plus b squared minus c squared. So we see that c squared is equal to a minus b squared. Okay, so it's a bit better. I mean, it simplifies a tiny bit, but actually delta is minus 1 also, of course, which was also sort of secretly, and for even length, this was also kind of isotropic, right? Remember, there was this way of sending minus delta to plus delta. So you get plus or minus, which is minus or plus. So these two cases are somehow a little bit simpler at the level of this formula. But you know, I mean, the isotropic point is not really too much simpler, really. So the bit on that, the computation is not, if you do want to do it, you should just do it for general delta. You have to write a few deltas, but otherwise it's not harder. Everything is exactly the same. So there's, from the sort of computational point of view, for doing all these proofs, it really doesn't matter. The difference will be, so maybe I can also mention this. So I said, let's assume this. Well, actually, it just works. So what you can do, there's a little exercise. If you take A of u to be, let's say, the sinh or whatever of u plus eta, and B of u the sinh of u, and C of u the sinh of eta. If you want, we can add our overall scaling R. Then you can check that this is delta is, so delta tilde is actually only depends on eta. And you can compute the value. It clearly has an overall R, and then there's the U direction, which is kind of separate from this. And maybe what we can also briefly do, really related to this part and not what I want to talk about next week, is we can quickly draw a phase diagram. So since the overall scalings are not so important, let's draw A over C and B over C. And here is the value 0. For physical reasons, these weights should be positive because the energies are real. And then it goes to infinity. So here there's maybe 1. And then we go on. So the phase diagram turns out to look as follows. There are a few different phases. So here are lines which just have slope 1. So this goes 2, and well, here it's also 2, whatever. So there's these different phases. They have physical interpretations. So this one is called anti-ferro, but now electric. Remember from last time, we are thinking about dipoles in electric. This one is ferroelectric. This one is ferroelectric, and this one is, I think it's called disordered. This line here, so now we can compute values of delta because they only depend on these ratios. This line here has delta is 1, maybe 1 minus 1 in my conventions. This line here has delta is 1. This line here also has delta is 1. Delta is 0. It's just a circle around the origin of radius 1. And then all the other lines of constant delta, they kind of look like this. But they're going to be kind of, I don't know, looking more or less like that. Here, instead, they look like this. Here, I actually thought about this for a long time. Do you want to be like this? Do you remember? I don't know. They're also something, whatever. Easy to, I mean, you can compute it easily, or you can ask Mathematica to draw it. So this ferroelectric one is the regime which is highly polarized. So our kind of bad example where we have so this is dominated. So remember, so here what you can see this contains in particular A going to infinity compared to B and C, which can go very far in this direction. And in that case, the partition function is dominated by the configuration which has only A's. And last time we actually already looked a little bit at this, is the smallest possible change we can make. So if we have our partition function which only contains A's, like this, then the smallest change we can make is actually rather big. It's kind of a macroscopic change. We can kind of flip a spin, make a thick edge here, but then we have to do it all the way around. So it immediately has a very big kind of step in the way. So this is a very gapped regime, and it contains this is our kind of special easy case to understand. Here it's similar, but B is now dominating. So this was the example where instead we have everything, all thick lines horizontally, let's say, and all empty lines vertically, and then the minimal change you can do is add one extra line or remove one of the lines, which again is macroscopic. So these two really behave the same. These are related by just swapping A and B. And last time we talked about this, it's related to some maybe rotation of the vertices in the arrow picture. So it shouldn't affect physics. Now this here, this regime, so this has the order parameter which is the polarization. This is net polarized, these two, in some direction. This regime here has zero net, well, all the rest has zero net polarization, but this instead has net staggered polarization. So this is the case that we were doing remember the exercise about the graphical computation of the partition function. That is happening deep in here, where the ground state is the one where you have kind of these staircases of orange lines going, well, they're my thick lines, but now I decided to do orange. They look like this, blah, blah, blah. So this is a ground state, and then there's one which is translated by one in any direction. And here we can do very small changes because we can just flip this to go here. So it's a very small and local phase. So here, there is much more stuff happening close to the ground state. And so actually, this is an infinite order phase transition. This was found by Leap, so it's a very nice result. So the free energy, I think, or the partition has an essential, it has a, an e to the minus 1 over x squared type of behavior. And it's kind of smooth, but
it's the Kosterlitz towers.
Yes, right. It's a KT type, a Kosterlitz kind of phase transition. So it's in this model as well. So it's nice actually. We have an integrable model which has this behavior. And then here,
But what happens at the 2 points where the 3 phases?
these.
Yes.
Well, B is 0. So we only have A and C,
And the kernel.
and we also have A and C are equal. So what can happen? Not too much, I guess. I haven't really thought about this, but I suppose I don't. Let's think about this in a moment. First, so here I have to. Okay, I do this off the top of my mind. I think this is a first order phase transition, but maybe it's second order. Do you remember or? So I think it's first order, but maybe second. Anyway, known and then easy to compute. Well, I mean, Leave did it. Right, so why did we do this? Well, so here's the point. So we also have our ice point where everybody is equal. So that's the point here. This is ice, or infinite temperature at 1,1. And so the F model, remember the F model, it sits here. The KDP model goes, I suppose it goes like this. Or it can also go like this. Remember, it didn't really matter, these two. And that's so this is the three special cases that need considered. And Sutherland really finds the results for all values of ABC. And right, so here we have the free fermion line, which is of course a very special case. So okay, so here we understand the parameterization. I've removed R by considering ratios. I've drawn surfaces of constant delta. So the spectral parameter, geometric, what it does is it parameterizes stuff along this line. So going here, that's what the spectral parameter parameterizes. And so F model has a very special symmetric kind of version of this, but in fact you could do variations at the same delta, and this is what Sutherland did by varying mu, and really everything works very well. Maybe I can also say, I don't know if I did it last time, so there's also a special case which is here, which is delta is minus a half. So this is for odd length, this is the point where all sorts of cool stuff happens. So it's sometimes called the supersymmetric point because it has some sort of discrete n equals 2 or 2,2 maybe supersymmetry on the lattice. And it's also a combinatorial point. So all the Hasselhoff, Stroganov stuff, and Philippe really worked on this. So this was really a big activity. And it's very, very cool. So this is a very special combinatorial point. This value 1/2 here. Is this true? I think that's the aspect diamond. Is that right? Right. So delta is 1/2. This is, if you like, combinatorics, then this is where the aspect diamond happens. No, it cannot be. It has to be delta 0. Because it's free fermion, no? Because we have the Johansson. Is that true? Well, let me first write it. So there's something called the aspect diamond. And it's also very special. I think it's 1/2 somehow, but I don't know. Okay, we have to think about it for a second. So this is another special point. So there are some special points, and really this F model is much richer than KDP.
Yeah, it has enumeration, so I guess C square root of 2.
Maybe it's 1 over square root of 2 then. So probably it's something like this. That's right. Yes, I think that's true. Yes. All right. So this is the phase diagram, and it was obtained by beta ansatz, like what we discussed here. And I think we know enough about the 6 vertex model. So next time we can go algebra.
I will not be next time, unfortunately. So the x-axis limit, can you point it in the diagram?
Mm-hmm. So it depends on whether you want ferromagnetic or anti-ferromagnetic, but it's either this line. It's precisely the critical line where this phase transition happens.
Which one?
Well, this is doesn't matter, I guess. It's either one. So ferromagnetic is either this one or this one. Anti-ferromagnetic is this one here. So how does it differ? Well, it swaps A and B. So what you can do is you can change your parameterization a little bit. Here I've made it so you can do +1/2 eta and -1/2 eta. It's also okay. And then it looks a bit more symmetric, and it's kind of relating u to minus u, I guess. I mean, it's some simple thing here. Right. So from the 6 vertex model point of view, we understand that they're precisely the critical lines in this phase diagram. But of course, this whole 6 vertex model is secretly some sort of, well, this whole phase is critical. So not just these boundaries, but this is all critical. Just like the planar regime was for example. The gapless. Right, so here the order parameter, I was talking about order parameter. Here the order parameter is staggered polarization, so you kind of measure the spins with a sign as you alternate. And here, so this is ordered in that sense. And then this ordered regime is the one that's not kind of ordered along either according to either definition. So you have lots of small fluctuations. Okay, I think it's only time to go on.